Okay, let us continue our session. And so the next talk by Yana Teplitskaya, and she will talk about some Steiner trees. Yana, please.
Thank you very much for the opportunity to talk here. Please feel free to interrupt me and ask questions by voice, not in the chat. I think I will not see the chat during the talk. I will talk about Steiner tree problem. It is a problem how to connect points by the shortest way. Usually we work in the plane and have the finite number of points. For example, if we have 2 points, the solution of Steiner tree problem is just a segment. We will look for the smallest one-dimensional Hausdorff measure, but if you are not familiar with this thing, you can think about it just as about length. In our problems, it usually the same thing. So there are a lot of statements of Steiner tree problem. One of these is following. Let we have a compact subset C in Euclidean space. Then we are looking for such a closed set S that the union of S and C is connected, and the one-dimensional Hausdorff measure of S is minimal. If C is totally disconnected, for example, if it is a finite set of points, then clearly the set S should be connected. We usually will work with this. One more simple example is how Steiner tree problem for 3 points. If we have such 3 points, A, B, and C, that triangle ABC doesn't have any angles more than 2 pi divided by 3, then the solution of Steiner problem will be the tripod. How to construct the tripod? You can choose randomly 2 points, for example, B and C, as in this picture. Then you construct a regular one of 2 regular triangle. Then you draw the circle around this triangle and intersect the segment of this third vertex of this regular triangle with the third vertex A. The point which we get named Torricelli point, it is unique, and it is the same for every pairs of points. So if you would take A and B and construct a triangle A, B, and something so on, then you will get the same point. All the angles, let's call the Torricelli point F, and then all angles AFC, CFB, and BFA are equal to each other and equal to 2 pi divided by 3. And this point is unique, and the sum of these 3 segments AF, FC, and FB will be the smallest one. If we will take 4 points, we also can construct the Steiner tree by choosing 2 points, then making the regular triangle and so on. But there will be 2 different network, 2 different trees with the same structure. So there could be these points, blue points, connected with the B and C and A and D. And if A, B, C, and D would be the vertices of square, then these 2 trees will have the same length, say Faust measure. It means that sometimes we don't have the uniqueness. So for example, for vertices of the square, we have two Steiner trees, two solutions of Steiner problem. There are some things which we know about Steiner problem. We know that solution always exists, that solution cannot contain any loops, the images of circles. And we know that every point of Steiner tree outside the given set could be, can have one of two neighborhoods. It can be a center of regular tripod as a Torricelli point, for example, and it can be just as center of a segment. That's almost all points. We also know that such points that they are center of regular tripod, we will call them branching points. We know that the number cannot be more than countable. The most interesting Steiner trees are such Steiner trees that tree without given set is connected. In other words, it means that there is no vertices of degree 2, only of degree 1 and 3, and all vertices of the set S of C of given set can have only degree 1. It also means that the segments of full Steiner tree can have only 3 directions, because the direction can change only in the branching points and only by 2 pi divided by 3. So as I have said, the number of branching points cannot be more than countable, and there is also exists an example of countable number. So in the picture, we can see the fractal set, the fractal set of vertices of binary tree, such that its Steiner tree has infinite number, is unique, and has infinite countable number of branching points. So all the picture, all angles are equal to 2 pi divided by 3, and we can ask the coefficients which are equal to the scalar at every step of constructing the tree. I mean, y1, 1, 2 divided by y0, y1, 1. We can ask these coefficients to be whatever we want, but they should be sufficiently small. If every coefficient, every scalars are equal to 1 divided by 300, it is enough. And there is one more thing that is interesting to say about full trees. If we have a such full tree, let's consider a full tree. Then if there exists such a small epsilon that we can prolong every segments by a small segment with length epsilon, such that the new set is also Steiner tree, then we said that the given tree has adding property. And the theorem is that almost all Steiner trees have adding property. I mean that if set of vertices of Steiner tree is such that Steiner tree is unique, and it is true for all vertices in neighborhood of the given one, then this is true, and Steiner tree has hidden property. The simple example of this situation is a tripod. If you have a regular tripod, which of course is a Steiner tree for its vertices, you can prolong every segment a bit, and you will have a tripod, which will be also the Steiner tree for its vertices. So every tripod with the angles 2 pi divided by 3 is a Steiner tree with hidden property. And we know that almost all Steiner tree are unique. So the dimension of the set with non-unique Steiner trees have the dimension 2 m minus 1, where m is the number of vertices. And let's see what is going on if the condition doesn't hold. And the simplest case when the uniqueness doesn't hold is vertices of the square. And they have 2 Steiner trees, a dotted one and just a segments one. And if we prolong it a bit, then you can see the right picture. Steiner trees will change. So at least a Steiner tree for a square doesn't have hidden property. Thank you for your attention. I finished my talk.
Thank you for your talk. Does somebody have a question?
Yana, may I ask you the question?
Yeah.
In these pictures, when you have a very, very small length of edges, is it possible to estimate the order of the, maybe if you take an exponent of their length, it has some limit or something like this? So the rate of decreasing of edges, length of edges.
I think that I do not know such estimates. There are some. Yeah. So the simple question is we don't know any estimates. But usually, if you will to search circles that they not intersect, it is enough. Maybe you can you need.
But is it possible to?
Circles, not.
So the question is it linear or no? No, maybe if you take the logarithm of this number with some base less than 1. So or maybe maybe another question. If you take the quotient of 2 consecutive edges, is it bounded or not, or something like this? Did you study some questions or not? Just the question.
I'm sorry, I don't understand. So we have a sequence of segments.
You look at each stage. You have edges of smaller and smaller and smaller. If you start
here, right? You are talking about this. I didn't understand. Okay.
Yes, and you take the quotients of length of each edge and divide by next edge, which is smaller. The question is, does this quotient tends to some fixed number, or is it bounded or not?
Now I got the question. So there were 3 different theorems, as you can see at the title of theorem at the slide. So the last result is that you can just take the equal coefficients.
Equal.
It is also, if you took, I don't know, all scales equal to 1 divided 300, then it will work.
Okay.
And of course, you can take everything which is smaller than it.
Mhm.
And
Okay, thank
yeah.
Thank you. Thank you.
Can I
So
ask
for
what
not
is
equal,
group?
it also works. It is easier to prove for the coefficients which first go to 0.
Okay, I have a question, please.
Yeah.
Okay,
Yes,
I'd like to know if Steiner trees are in any way related to Steiner triple systems. I don't know. Steiner triple systems. We have them in quasi groups and loops. I don't know if your Steiner trees, I don't know if Steiner trees are in any way related to Steiner triple systems.
I think there's just one man.
Okay.
There is no connection.
Okay, thank you.
As far as I know. No.
And can I ask what is group of automorphism of Steiner tree? Is it some isometric group?
I cannot answer. Sorry.
Is
sorry.
it self-similar group? Maybe some class of group? Can you describe?
I don't know, and I never saw works about it.
Oh, it's good. It's good. So we have to know what we can think about. Okay.
We usually
Does
think
have-
about the complex space of if your point is equal to the set of terminals, and then we know what is going on. But it is not in the terms of group.
May I ask a question,
Thank
a quick
you.
question? So, Yana, if I understand, so one of the theorems which you showed, it effectively it's saying that you have, this one. This one at the bottom of page. So, so your you have like m tuple of points on the plane, right? So essentially what the theorem is saying that the set of bad m tuples is like a hypersurface. It has codimension 1, yeah. And is it like some nice hypersurface, like algebraic or something, say for a fixed m?
It is not very bad. We have a work. We have a work about how the set of the space of this works. So it will be. Yeah. So I cannot I cannot explain shortly how it looks like, but for example, we know that we can think about the topological class of Steiner trees, and we know that set of search points that Steiner trees have the same topological class is connected and good. And
right.
yeah, on all spaces, that's these spaces.
So so I assume for m equals 4, this set is completely described. It is fully known.
It is not hard to describe. So it has dimension 7, and we understand what is the position of vertices, not only this vertices of square looks like if they don't have unique Steiner tree. But I think that there are a lot of open questions here that nobody's interested.
Yeah. would be interesting to know if it's like sort of semi-algebraic or something. Yeah, thank you.
I think that it is open. And yeah, about this theorem, I formulated it this way. And in our papers, it uses another conception of maximal distance minimizers.